So we're going to have two back-to-back talks here. Sean Ahern from CEI is going to talk about Ensight and SWR, and then John Stone's going to jump up and talk about VMD. So enjoy.
Sounds good. Thanks very much, Jim. So let's dive right in here. What have we been up to with Ensight with OpenSWR? So first, a couple quick introductions. You guys know what OpenSWR is. Is there anything here we don't have? Intel wanted me to make sure I mentioned this is alpha software. Hasn't been fully released yet. Looking at functionality, we'll look at performance improvements later. I do talk in this talk about features, but then I also do look at performance. We're actually pretty happy with it. And primarily, we've seen a lot of performance advantages over Mesa. Let's see. I will say that what I'm going to present here is all the performance on the front end, on just a single client running on a desktop. How does that compare? Doing the parallel rendering work, which is what you're seeing on that back end system. We're still working through that. I don't have performance numbers or testing or anything like that. That's actually the first time we've had it going. Is for this demo. So this talk is just going to focus on the front end. So what is Ensight? It's a tool that's designed for engineering visualization primarily. It's computer simulations, experiments, but our primary markets are engineering. CFD, finite element analysis, turbo machinery, things like that. It's got a lot of very deep, a lot of algorithms for deep engineering analysis and plots and so forth. Operates well in parallel. It's been around for 20-odd years. Pretty successful. So what do we do with OpenGL? So the current version of Ensight is version 10.1. And we are primarily doing display lists. We do have some frame buffer operations and some shaders. We're using the fixed function pipeline tremendously. We're not doing any vertex programs right now. So limited use of shaders. That's going to be changing in the next year. We're revamping honestly our entire OpenGL pipeline. So it's 2.1. So it works very well with OpenSWR. We kind of get up to 3.3. We do have the ability to turn on and off different features depending on what we find with the graphics card. We've had to do that for historical compatibility with various cards. So we end up having two paths. If we have a GPU, we've got this high capacity path. If we don't have a GPU, we've been using Mesa, and we go, well, crap, let's turn off all of this stuff. And so if you've got the high capability path, you've got all sorts of really great stuff going on. Honestly, we do a lot of stuff with OpenGL. We've got depth peeling, which this is really neat. It allows us to be able to do opaque geometry, transparent, volume rendering, and it's all pixel accurate transparency. We don't have to worry a lot about the sorting. We figure out where each of the depth peels are, and we do volume rendering between those and blending through with a configurable depth. Dynamic highlighting, hardware picking, a lot of interesting things going on, and those all disappear when you're using something like Mesa, something that isn't as capable. That's actually one of the things we're very excited about with SWR is being able to turn some of these things back on, even though we're going to be going down a software path. So to give an example of some of that, here's a couple renderings that we have of kind of what we're doing with OpenGL. So this is volume rendering, it's a 1D transfer function. You can have opaque or transparent geometry as much as you want within that same scene. We have pick buffers. So as we render things, we've got an object buffer. It's an auxiliary buffer that we render into. It's an FBO, so that we can very quickly identify when the user clicks on something or they drag something, we know what object is at that pixel based upon that frame buffer object. So it allows us to do very easy interactions for the user. We use the overlay plane a lot for all of these legends and queries and things like that, and then those are interactive. And then I forgot about this one. Inside the OpenGL window, we've got all sorts of extra viewports. They have their own context, they have their own views, and so this all needs to be done at the same time. And then finally, we use a tiling system for OpenGL off-screen rendering so that you can save images at arbitrary resolutions. So we chunk them up, we render each one of them into its own separate frame buffer, read them back out, and tile them together so that we're not limited in the amount of pixels that we can, or we're limited by how much you can store in the file format, not by what the OpenGL pipeline can handle. So we're pushing the OpenGL pipeline fairly hard, even with just the fixed function pipeline. So we've got full screen anti-aliasing through a shader. This one's kind of neat. Our users like this a lot. When you're mousing over the problem, because we've got this object buffer, as you put your mouse over the over the wing, for instance, the wing turns yellow and all the other stuff kind of darkens just a little bit, and that happens as you mouse over the whole problem. And it's just it's simply identifying what you've hit inside that object buffer. Kind of neat. I mean, users like it. Particle rendering. We in 10.1 we've got an imposter-based particle rendering. A lot of tools have this, but obviously you need a pixel shader to be able to do that. This was done. So most of these images were SWR kinds of things. This one was done on the GPU. Obviously, left one was SWR, right one was the GPU. So as I said, the things that we want to look at here are what is the capability? What type of capabilities do we have for SWR versus what we have right now with things like NVIDIA or AMD? And then let's look at what the performance is, because obviously we'd like the best of both. We'd like to be able to do all of these cool high capability things, but we'd like to be able to get decent performance as well. So we looked at 3 different paths. We looked at just the regular OpenGL driver with NVIDIA or AMD. We looked at the Gallium driver, and we looked at LLVM pipe. So first, let's take a look at capability. Just about everything's working, honestly. We've got all the hardware picking, dynamic highlighting, we've got overlay planes and 3D buffers, anti-aliasing, the depth peeling. All this stuff works great. We're very happy to see that this worked out of the box. There are things that aren't working yet, and we're certainly working on this with Intel. The imposter-based particle rendering, we need OpenGL 3.3. We're close there. We don't have volume rendering, either native grid or resampled grid. We have not explored this. We don't know what it is yet. It's probably related to FBOs. FBOs have been a source of problems for us, and in the demo, like we're running back there, I've turned off our use of FBOs. So when you mouse over things, you will not see that highlighting. We think we've got some workarounds. Like I said, we're working with Bruce and folks, and so this is an active area of work. And wireframes are also sometimes opaque. This was one that took a little bit to look at. I think Intel folks know about this. On the left is with the GPU. I then ran exactly the same thing using LLVM pipe. Looks exactly the same. I ran it with SWR, and suddenly all my polygons went opaque. It may be how we're running the pipeline, but this is one where I don't think so. So there are small things like this. This isn't a huge issue, but we've run into a couple little things like this. But by and large, we're very happy with the way this has turned out. So as Jim mentioned, I think it was Jim mentioned at the beginning, who was talking? I can't remember. Yeah, Bruce was talking about the different testing. We have our nightly test suite that we run, which honestly it mostly tests a lot of our readers and our data processing pipeline. It doesn't really push the rendering. It's Mesa based, so it's not doing a lot of these advanced things, but it's certainly something to throw at SWR and see how it does. And it actually worked pretty well. When we say failed, all we say is that the difference in the images and the queries and things like that went above some threshold, and we chose 10%. So 10.1% will be failed, where 9.9 is succeeded. So it's a little bit fuzzy when we said that. I think we said it was like 15 tests failed. I'll show you something on the next slide. It's actually very, very good. Nothing crashed. We're happy to see that. At the very first thing that we did, we said, okay, does the number of tests that work, did it change? And no, it was fine. And honestly speaking, this is our biggest difference. And I doubt you can see it with this projector. But let me see, is there a pointer here? Is it a pointer? So this is the reference image, and this is what was rendered with either LLVM pipe or what was the previous one called? What's the regular Mesa before LLVM pipe? I can't remember what it's called. What's that? No, there's a number of them. This was as a reference image. This is what SWR spat out. And you'll notice this orange is more intense than this, and this yellow is more intense here. It has to do with line rasterization. The way Mesa rasterizes lines and the way SWR rasterizes lines are different. And I'll be honest, I actually think that this is a better image. So when we say that the tests failed, the tests were different, but I actually think that we should probably rebaseline them and consider this one to be the reference image. So we're actually very happy with the way those all turned out. So we then dove into performance. And so we had two different systems that we ran on. One was an older system with 4 cores. Another one was a newer system with 24. This system had an AMD. This other one had a Quadro. It was interesting looking at this. The fact that we ran this on 2 completely different machines, especially with the core difference, made a huge difference in our performance. As you'll see, I liked this a lot. And again, we looked at GPU, LLVM pipe, and SWR. So here we go. So we just looked at some test models. So we've got the Lucy, the Dragon, and the Buddha. And in this case, we are looking at it's frames per second. So longer is better. And the blue is the GPU, the orange is SWR, and green is LLVM pipe. And in this case, this was let me see, which order do I have these in? This was machine. Hold on a second. That's right. So yeah, there we go. So this is a lower powered machine, and what we found almost across the box. So certainly GPU wins. You know, aren't saying that it's going to beat the GPU. These are the numbers that we really want to compare, and what we found is almost across the board, SWR was about a 2x performance increase over LLVM pipe. On the machine with more cores, we got a much different number here. So what we were getting was about a factor of 5 to almost 10 performance difference on that higher-end machine with more cores. You're happy to see that. This was a test that was run on some real-world problems that we had. This was only run on the system, on the first system, on the slower system. And again, we got the same type of results, which was about 2x performance difference between SWR and LLVM pipe. I will say quality was exactly the same, so happy about that. The only reason I wasn't able to rerun these on the higher end machine is the guy who has the data, his first child was born, and I wasn't able to contact him and get the data and rerun this before I had to give this talk. But I expect that it would have been similar results to what we saw here. Yeah, poor excuse, right? This one actually I consider to be the most interesting one. This is, Ensight has built into it a performance benchmark that sends polygons down the pipeline. We have a synthetic reader that can just create lots and lots of data. And it creates more and more data, sends polygons down the pipeline, and renders them in different ways. It renders them in wireframe, immediate mode, normals, flat shaded, Garot shaded, transparent, and just keeps shoving more and more polygons down the pipeline, and looks not at what the frame rate was, but looks at what is the polygons per second rate. This is similar to what we saw earlier. And this is what we have on the GPU. And so we'll look at the fast one. This is solid smooth triangles. I crank up the polygons here. Here's 10 million. Once we're getting somewhere between 10 and 100 million, the performance tanks suddenly. I think what we're probably running into is possibly PCI bandwidth is my guess, yeah. or memory on the card. Either way, that's the cliff at which point the GPU falls off. Somewhere around 600 million polygons per second. So here's SWR. Now, SWR I find interesting because it just keeps going up and to the right. We just kept pumping polygons into it, and its polygons per second kept going up and up. Now, we're talking order of magnitude less here. We're talking tens of millions of polygons versus hundreds of millions of polygons, but that's okay. Especially compared to LLVM pipe, the y-axis barely got into the millions. And you can see the number of polygons. We stopped testing. We stopped shoving more polygons down the pipeline when it was clear that it can't keep up. But the part that I find interesting is what is the fast path? On the GPU, our solid polygons rendered with smooth lighting were by far the fastest pathway, whereas with SWR it was wireframe. Now the other ones were all sort of in here, and then you've got this slower path down here, and that was our immediate mode and what was purple? Transparent. So these are kind of interesting. I love the fact that these curves just keep going up to the right and don't fall off. So they're probably the most interesting data that we have. And it's in conformance with, there was a similar plot earlier this afternoon that showed similar types of performance continuing to go up as you crank the number of polygons up. So the next thing we're going to be looking at is shaders, because we've pretty much turned these off. This is where we're going in the future. We want to look at, given that we're moving towards a lot of shaders in our 10.2 release this coming year, this is where we're going to be doing a lot of our work. We also there's a lot of work that we need to do to be able to move our pipeline entirely over to OpenGL 3.3 core profile. It's work that we need to do anyway. So we are going to be, and going along with this, we're getting rid of our display lists. Everything's going to VBOs. We're going to be doing a lot of shader work, physically based lighting, a lot of textures, lighting models, especially metals. A lot of our customers they model metal things, and they want these to look pretty good. We are going to be doing a lot of texture work as well. So vertex shaders, pixel shaders, and so on. So this is going to be important for us to have going well in OpenSWR. And our plan is, wow, that's an eye chart. Our plan is to continue our testing and move toward releasing Ensight. Our hope is our next commercial version, we will be shipping it with OpenSWR as our primary software rendering path. So let's see. Yeah, we're very happy working with the Intel's development team. This has been great. There have been issues that we've identified, and we're still working on it. We end up having to, we end up running into a bunch of these. A good portion of them may well be ours, but we are working a lot with this. Our plan is that whenever you are lacking a GPU, you're on a back end, you're on some cluster, and there's no GPUs on the back end, SWR is how we do all of our rendering that way. Don't talk to an X server. And we will get, especially for a high multi-core system, we're going to get dramatic rendering speed improvements versus what we have currently, having deployed Mesa. And hopefully, and I want to stress this, we can turn back on a lot of these high capability things that we've turned off because it's Mesa, all of these FBO type of activities. So I said eventual. My hope is that it will be, the 10.2 release would be this summer. Is kind of what we're aiming for. And this would be released to all customers. And that's it.